Thank you. Today I'm going to be talking about a connection between braids and knots by algebraic means. This is a joint work with Andrei Ryabichev, who will give a talk in the day after tomorrow. And basically, in our work, we build on previous works and results of Andrei Valerievich, Andrei Malyutin, and we use algebraic functions on braid groups to show that in some nice cases, anomalies that exist on the bridge between knot theory and braid theory disappear. These anomalies disappear, and I will present to you these anomalies and show how to use pseudo characters to obtain results of this kind. Okay, the main object today is the braid groups, which have many different equivalent definitions. And today I'll be mainly focused on two of them as isotopic classes of curves in the cylinder and as the mapping class groups of a disk with punctures or marked points, as we today we've already discussed this topic a little bit, mapping class groups, I mean. Let me briefly remind you the main connection, the main connector between braids and knots. Namely, the operation of the closure, Alexandera closure, that maps braids to knots and links. And Alexandera theorem states that any knot or link can be presented as a closed braid, something like that. And in fact, any knot or link can have many different expressions as a closed braid on many different numbers of strands. So for each knot or link, we have an infinite number of braid representatives from different braid groups on different number of strands. And a theorem of Markov gives necessary and sufficient conditions for two braids to yield the same closure. And in fact, I will not state it here explicitly, but basically there are two kinds of local moves that you can perform on braids. Опечатка. So basically there are two moves that preserve the closure of a braid. The first one is conjugation in the braid group, and the second one is the so-called stabilization. And these are the so-called Markov moves, and any two braids can be related by these moves if they represent the same knot and link. And I will be focus on the first type of move, conjugation. And to study conjugation properly, we need to refer to invariance of conjugation in the braid groups. And the main tool here today is the so-called pseudo characters or quasimorphisms. Here's the definition. A function on a group is a character or quasimorphism if it is a real valued function that is almost a homomorphism up to a bounded error, up to a fixed constant c such that phi of xy is almost phi of x plus phi of y. And a character is called pseudo character if it is if it satisfies this property, if it is homogeneous. And in fact, any homogeneous, any such function is constant on conjugacy classes of the group. That is why we are interested in pseudo-characters on the braid group. So the first example of pseudo-characters dates back to the work of Andrei Malutin. He defined a pseudo-character omega, which is called the twist number of braids, the twist number. And the defect of the twist number, this constant, is equal to 1, in fact. So let me briefly give a feeling about this invariant. For this, I will use the so-called Darnois order. It is a total order on the set of all braids with a given number of strands on the braid group. I'll use it just as a black box. So imagine that we put every element of the braid group on the real line. Darnois order yields such an image. And then consider this special type of a braid, which is called the central braid, and consider all of its powers. These powers give a zero-dimensional grid on the real line, and we can compare every braid with these intervals between the powers of the central braid. And basically, this quantity, I mean, where the braid lies in the Darnois order, is something like the number of full twists that the braid contains. Like, if a braid is more than the central braid, then it contains a full twist. But in this example, it contains a full twist, but it does not contain two full twists. So this quantity, I mean, just where the braid, in which interval the braid is. This quantity is called антие-Darnois. Darnois floor function. And to obtain the twist number of Andrei Malutin, we need to perform the so-called homogenization. And for this, to obtain this homogenization, you simply ask, okay, my braid is somewhere here, like its Darnois floor is equal to 1, but is it more closer to this braid, or it is closer to that braid? And for this, you need to simply zoom your scale. You need to square your braid. Then you need to compare in which interval your braid is, the square of the braid is. That's why we take the floor of the square, say, and then divide it by 2. So if you take this limit, you will obtain not an integer, but a real number. In fact, this real number is a rational number, but I will not explain why it is so. So this number is called the twist number of a braid. And the Darnois floor is a character, and the twist number is a pseudo-character. Okay, now I'll go to the part where I explain you 3 types of anomalies in the connection between knots and braids, and how the twist number allows to evade these anomalies. So the main phenomenon, the first type of phenomenon, is that the closure of a complex braid may actually be a trivial knot, say a trivial knot. Or the closure of a braid that looks irreducible may be a link that is split. Or or say a composite link that contains local nodes. So the first result of Andrei Valerievich states that if a braid, if the twist number of a braid is at least 1, then there is no such possibility. And moreover, the closure of this braid is a prime link. So these anomalies, they are somewhere for braids that are not sufficiently twisted. Okay, then I will present you a generalization by Tetsuo Ita that states that, moreover, you not only obtain for sufficiently twisted braids, you not only obtain non-trivial links or prime links, but even if the braid is sufficiently twisted, then the closure is sufficiently complicated in topological sense, say relative to the genus of the Seifert surface. If G free of the link is the minimal genus of a Seifert surface, then as soon as the braid is twisted enough, the genus is huge. This linear bound gives the precise answer to this this idea. And I would like also to mention another result about four-dimensional topology. If instead of a free genus you consider the so-called slice genus, this is the minimal genus of a surface that bounds the closure of a braid, where the surface lies in the four-ball. Then we have this type of bound, and indeed, sufficiently twisted braid closes to a very complicated knot or link relative to the four-dimensional topology. N is the number of strands. Okay, this was the first category. Then the second category. The second category is minimal representatives of knots and links. Minimal with respect to the number of strands. You see, for every knot or link, there might be many different representatives, and even on the least number of strands, these representatives may be non-conjugate. And this is an anomaly. But in fact, for sufficiently twisted braids, this is not the case. Namely, if the twist number is at least the number of strands, then, first of all, this braid cannot be presented as, the closure cannot be presented as the closed braid with the fewer number of strands. And secondly, this result states that if you close sufficiently twisted braid, then this braid is minimal relative to the number of strands. You cannot represent this link in more simple terms. And then I will state the result that states that sufficiently twisted braids, for sufficiently twisted braids, strands, and then I'll show you the result that states that for sufficiently twisted braids, this anomaly also does not show up. And for this, I will introduce a constant that depends on the number of strands. I will not give you the precise estimate of this constant. In fact, it is unknown, but it is R of n. It is at least n. It is at least n, and I think that I conjecture that there is a polynomial bound on R of n in terms of n. But there is no information in the literature. So we say that a braid is sufficiently twisted or strongly twisted if the twist number is at least R of n. And Andreevich and Nikitorevich Nizetayev proved that for strongly twisted braids, the closures of strongly twisted braids are equal if and only if these braids are conjugate. So this is the second category where the twist number shows that there are no such anomalies. And for the third category, I'll need to recall some geometric terms very briefly. First, I need the Nielsen-Thurston classification for surface homeomorphisms, that every surface homeomorphism is either finite order, periodic, preserves a number of preserves a multi-curve, reducible, or is pseudo-nosov. This means that it has a very rich structure and very interesting properties. It contracts in one direction and expands in another direction. This is for surface homeomorphisms, and the similar result. There is a similar result for braids, because braids are homeomorphisms of the disk. But for this, for braids, the classification, the Nielsen-Thurston classification, is a little bit different. Any braid is either periodic, and this means that it's conjugate to a power of either this braid or this braid, or it is reducible. This means that this braid is a braiding of external braid and several internal braids inside it. Or a braid is pseudo-nosov, which means that I will not explain it here. So the third type, to present the result, I need to show you the guiding star of this category. For manifolds that fiber over the circle, as is well known for three-dimensional manifolds, there is a geometrization theorem, which states that there are geometric structures on every free manifold. And this theorem states, in this particular case, that the geometry of a free manifold corresponds to the dynamics of its monodromy. Precisely as it is stated here. And for knots, geometrization theorem states that every knot corresponds to one of three geometric types. And we can present knots and links as closed braids, and we can ask whether geometry of a knot or a link corresponds to the dynamical type of the braid. This is the question that I would like you to answer. And once again, any knot, there is a geometric classification of knots. Any knot is either a torus knot, satellite knot, or hyperbolic knot. And we wonder whether dynamics of a braid reflects geometry of its closure. And the answer is, in general, there is no such correspondence between dynamics and geometry. Namely, the closure of a reducible braid may be a non-satellite knot, and the closure of a pseudo-nosov braid may be a non-hyperbolic knot, namely a torus knot or a satellite knot. However, for sufficiently twisted braids, there is a correspondence. If a knot is expressed as a closed braid whose twist number is at least 2, then these three types in the geometric classification and dynamical classification agree. So basically, I presented you 3 types of anomalies and showed how to use, and showed how to use the twist number to evade these anomalies. And I claim that any pseudo character on the braid groups can be used to provide similar bounds on complexity, sufficient conditions of the closure to be a prime link, and sufficient conditions for the correspondence between dynamical type and geometric type, the dynamical type of a braid and that type of the knot. Okay, let me skip this part where I explain technical details and show you these results, these new results with precise bounds. As you can see, in general, for any pseudo character, we have a bounds with respect to its defect. And here are some linear bounds, and we also have another a little. Okay, let's skip this part. So the main idea here is that pseudo characters are universal in knot theory, and actually it was noticed by Andrei Valerievich, also by Andrei Valerievich. Here is his result on primeness of links, and we extended this universality theorem on other results concerning the Nielsen-Thorsen classification and the genus knot, the genus of the closure, and these results about minimality and conjugacy. So that's it. Happy birthday, Andrei Valerievich. Я тут... Да. Например, в полном обороте антиедурна по определению равно единице, и мы будем вот этот предел считать, мы будем полный оборот возводить в m той степени, а потом делить на m. Такой самый простой пример. Да, на группах кос векторное пространство псевдохарактеров, вот их можно поточно складывать, умножать на константы вещественные, оно бесконечно мерное. И там есть разных много... А? Нет, не умножать, а складывать поточечно. Это бесконечно мерное пространство, там есть разные псевдохарактеры с геометрическим смыслом. Например, можно сигнатуру вычислять, можно смотреть на псевдохарактеры типа закрученности. Вот здесь вот они у работы Ивана Алексеевича и Владимира Шастина хорошо описаны. Это такие похожие штуки. А еще есть разные псевдохарактеры, которые обнуляются на любой периодической, на любой приводимой косе. То есть они не нулевые только на псевдоносовских. И они отражают, насколько сильно кривые запутываются, когда мы применяем псевдоносовскую косу. Насколько сильно вот этот темп роста сложности в комплексе кривых. И вот они, например, для них из вот результатов, которые я перечислял для закрученности, они для, значит, у кос, у которых маленькая закрученность, нулевая закрученность, эти псевдохарактеры могут принимать большое значение. Эти вот, которые я сказал. Они могут принимать большое значение. Поэтому эти результаты, которые я перечислил, они релевантны. То есть это не обобщение, они действительно обобщения. Есть косы, для которых они дают то, что закрученность не давала. Дефект, ты имеешь в виду? Вот у закрученности дефект равен единице. И есть теорема, например, что в классе хороших псевдохарактеров, вот я здесь не успел определить, что это такое ядерные псевдохарактеры, и еще с условием нумеровки, дефект это, закрученность это единственный псевдохарактер дефекта не больше, чем единица. То есть у всех остальных у них дефект больше будет, как правило. Поэтому будут хуже оценки.
А вот, допустим, у меня есть две косы, я хочу сравнить топологические замыкания. Я могу как-то привести их к другим косам с достаточной закрученностью, меняя топологического типа, чтобы использовать.
Да, то есть это как бы в этом и смысл, что мы берем, представитель замкнутой косы и смотрим, чтобы была получилась большая закрученность.
Есть какие-то движения или процедуры, которые из данной косы делают другую косу достаточной закрученности, но чтобы замыкание имело тоже топологический.
Или нет, как бы ослабить закрученность легко, а получить сильно закрученную форму.
Да.
И если было, то, видимо, выплатили просто.
Я с этой мыслью и спрашиваю.
Он у меня еще такой вопрос. У вас есть вопросы и есть список литературы. Это работа, где вопросы поставлены или где данный ответ?
На самом деле это я предлагал как суфлер для аудитории, чтобы можно было смотреть, что вам ближе. Например, здесь есть вопросы, что а какие еще инварианты узлов и зацеплений могут быть отражены на уровне псевдохарактеров? Там, допустим, гиперболический объем, он как-то виден. Допустим, верно ли, что если вы замыкаете псиновскую косу большой закрученности, то замыкание объем будет расти.
Сейчас, допустим, ссылка на гостиницу Фудживару.
Да.
Это ответ или там формулируется вопрос?
Нет, здесь скорее дополнительная информация, да. И, на самом деле я на первый вопрос уже ответил, это была моя задумка такая. Я уже ответил на этот вопрос, и я приложил ссылку вот на эти псевдохарактеры, которые обнуляются на периодических приводимых, а на псевдохарактерах они большие. Да, они построили такие псевдохарактеры.
Ну, все, на первый вопрос нет, еще раз благодарю за классика.